Okay, so we're starting a new unit. This new unit is called Thermodynamics, Kinetics, and Solutions. All three of those work really well together. We're going to start out by reviewing thermodynamics. We've talked about this before, and that is the study of changing heat flow. So when we're talking about thermodynamics, you need to understand what we're looking at. So reactions can be either an endothermic reaction or an exothermic reaction. An endothermic reaction is a reaction that absorbs energy in order for it to proceed, whereas an exothermic reaction is a reaction that releases energy. Exothermics are much more common. Exothermics are things like burning. Endothermics are like your instant ice pack. The other way you can tell about these is in an endothermic reaction, the energy or the heat or the joules or calories, that's going to be here on the reactant side. Whereas in an exothermic reaction, the energy, heat, or joules, or whatever unit of energy is going to be on the product side of the reaction. So those two ways are a way you can tell that, whether you have an exothermic or an endothermic reaction. The next term is called enthalpy. Enthalpy is an important concept in thermodynamics because it talks about the amount of energy. Enthalpy has a variable of H. Don't ask me why, but it's H. And we always talk about the delta H, the change in enthalpy. That's the amount of potential energy of the products relative to the reactants. Table I also calls this the heat of a reaction. So you want to reference table I for this. The way you calculate this is you calculate the potential energy of the products and subtract from that the potential energy of the reactants. Those terms would be given to you if you needed to calculate those, but that is not something you will need to do in Regents chemistry nor honors chemistry. That's something for AP chemistry. So the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. That's how you calculate it. Yours will just be found on table I. Thermodynamic reactions, one of the favorite things is to talk about the potential energy diagram. And in a potential energy diagram, there are two axes. The reaction mechanism is the x-axis. The y-axis is potential energy. So reaction mechanism can be thought of as the reaction proceeds, or maybe time. We've talked about this before as well. So that's the part of the bottom axis. This is a potential energy diagram for an endothermic reaction. Endothermic reactions have a positive delta H. The delta H is positive because the potential energy of the products is higher than the potential energy of the reactants. You end at higher potential energy than you start. Something that gets cold, something that absorbs energy, is going to have more potential energy at the end than at the beginning. That's why this hump goes up and then ends higher. Now this peak here at halfway point, that's called the activation energy. The activation energy is the amount of energy needed to start the reaction. This is the potential energy diagram for an exothermic reaction. Exothermic reactions have a negative delta H. The potential energy of the products is less than the reactants, so it's going to be negative. So if you take a number here, say 5, and this is 8, 5 minus 8 is going to be negative 3. So exothermic reactions are negative, whereas endothermic reactions are positive delta H's. Again, the activation energy is the amount of energy needed to start the reaction. In this case, you're going from the potential energy of the reactants up to this hump, and then the reaction proceeds. You can think of the activation energy as like when you rub a match against that abrasive pad. That little bit of activation energy starts the match up. If you didn't put that in, the match wouldn't spontaneously burst into flames, but you got to put energy into it. And that's what the activation energy is. It's that little bit of energy put into the reaction to make the reaction proceed. Without it, it won't. These are the two terms that are found on table I. Delta H of the reaction and delta H of the solution. Delta H of the reaction, that's just how much energy is given off by a reaction, whereas delta H of solution is how much energy is either given off or absorbed by something dissolving in water. So the top one is an actual chemical reaction, a chemical change. The bottom one is a physical change. And this is you can think of this as, burning something at the top versus like one of those instant ice packs. You smack the instant ice pack, you bust that little bubble inside, and that little bubble starts to dissolve the crystals. And what happens is it gets really cold. That's the enthalpy of a solution. So that one's an endothermic reaction. They get cold. Instant ice packs get cold. And the top one is the enthalpy of a reaction. If you talk about a instant hot pack, the little hot hands, when you open that up, it starts to react with oxygen in the air, and that's why it gets hot. That's the enthalpy of reaction. The bottom one is the enthalpy of solution. Those are two terms that are found on table I. Okay, so if you take a look in your review book, The New Hotness, I'd like you to read pages 90 through 92. Halfway down 92, I want you to stop where it says factors affecting rate of reaction. Everything before that is what I want you to read. Look at those diagrams. Look closely at those diagrams. I don't want you to do any questions later. We'll do the questions after we talk about rates of reactions and I do the introduction. Then we'll do the questions. But for now, just read those topics there, those couple pages, 90, 91, 92, half of 92. And we'll come back to it later. All right? If you have any questions, feel free to reach out to me through